All right, gang, I'm back. Part 2. You ready to do this? Ready to finish this thing off? Okay. Hybridization. The few people who really want to know what's going on. Actually, there's an even more complicated model called molecular orbital theory that I'm not even going to do. Okay, this one, the steering wheel turns, the convertible top goes down, the wheels turn, the doors open up, the trunk opens up, there's a little fire extinguisher in there. Molecular orbital theory. I'll let you read about it in the book, and if you're really fascinated, you can become a chemistry or physics major, and we'll tell you a lot more about it. Okay? Actually, you will learn about it in organic chemistry no matter what, but if you really want the details, you gotta hang in there even longer. All right, I'm gonna start the rest of this off explaining hybridization, explaining sigma and pi bonds, with a quote from C.S. Lewis, one of my favorite writers. Some of you probably know who C.S. Lewis is. Some of you may not know who C.S. Lewis is. C.S. Lewis is famous for writing the Narnia books. In fact, there's someone in this class who I'm guessing is probably named after a Narnia character. Just guessing because he's got an unusual name, who is famous in the Narnia books. So here's a quote from one of his books called Mere Christianity. Not normally a book one would quote in a chemistry class, but C.S. Lewis says, when scientists want to explain an atom, they give you a description out of which you can make that's supposed to be mental picture, not a metal picture, which you can make a mental picture. But then they warn you this picture is not what scientists actually believe. What the scientists actually believe is a mathematical formula. The pictures are only there to help you understand the formula. They're not true in the way that the formula is. Okay, so I'm setting you up here. I'm going to tell you, I'm going to give you some pictures. I'm going to draw some pictures to the best of my ability, which is rather limited. I'm going to draw some pictures. I'm wondering if this is even recording. It's not recording. It is recording. Okay, awesome. Don't want to spend another 30 minutes on it. All right, so what I'm doing is I'm setting up here. I'm telling you there's a mathematical reality that's underlying all this. And I'm going to draw some pictures and show you some pictures and point you to some pictures in the book and tell you, hopefully this will help you understand it. We want you to make a mental picture, but this is not what we actually believe. We believe the mathematical formula. The pictures are only there to help you understand the formula. Okay? So hang with me. SP hybridization. Let's go back to our example of beryllium dihydride. We had a Lewis structure for beryllium dihydride. And we found out, actually let's go back here, we found out the beryllium dihydride fails if we just think about electrons from hydrogen trying to share with electrons from beryllium. There are no electrons in the p orbitals to share. And even if somehow we could concoct them sharing electrons, they're not going to be at the right angle. They're going to be 90 degrees instead of 180 degrees. So we've got a fail on several levels. There are no electrons to share and the geometry is wrong. Therefore, my model's garbage. Okay, I need a better model. So how do we get around this problem of the model failing? So I'm going to try to be consistent here. I'm going to write down the atomic orbitals in orange and the hybrid orbitals in red. I probably will forget to do this at times. But here's the atomic orbital for beryllium dihydride. So this is a 2s2 configuration, 2p0. So what hybridization theory says is the s orbital combines with with one p orbital to form a new hybrid orbital. And that new hybrid orbital, and we promote one of these electrons into that empty one. So we end up with two new hybrid orbitals that we call an sp hybrid. And we still have two p orbitals left over that we haven't done anything with. So we have a, maybe instead of 2p, I'll just say p. We have a p orbital and we have two sp orbitals. We still have 4 orbitals though. Okay? So you notice we had 1, 2, 3, 4 atomic orbitals originally, and now we have 1, 2, 3, 4 orbitals, but one of them is a hybrid orbital. It's combined an s and a p orbital, and one of them and two of them are just regular old p orbitals. Now you might be saying, how does this help the problem? Oh, by the way, I need to put electrons in the hybrid orbitals. So I promote one of these electrons into this empty slot. So now I have these sp orbitals, and I have some empty p orbitals. This is for beryllium. Okay, beryllium has 2 electrons. This is how we're dealing with it. So you might be saying, well, how does this help the problem that you already had? Well, you already can see one way this might help the problem. One way this might help the problem is I've got electrons that are unpaired and have some slots in them that want to be paired. Okay, so that already helps the first problem that we saw. Here's how the second problem gets solved, and this is where C.S. Lewis comes into play. This is an s orbital. This is a p orbital. If we make a hybrid orbital, we combine those 2 orbitals. Now, there is a mathematical formula that I can use to describe an s orbital. Now, if you look at that, it's got an x, y, z axis. So this mathematical formula is going to have an x term in it, a y term in it, and a z term in it. And somehow you can graph that and make a sphere. Remember, that's called the boundary surface. That's where the electrons are within that, 90% of them are within that sphere. But there's actually a mathematical formula that can get generated that produces the shape of an s orbital. Just like there's a mathematical formula that describes the shape of a p orbital. This happens to be a py orbital. It's along the y-axis, so this happens to be called a py orbital. But it makes that dumbbell shape, which you know is a p orbital. Okay, here's where you're just going to have to believe me. We're not going to go through the math. I'm not going to give you the equations to form this. Remember when I passed around those orbital kits that Dr. Fogarty made? He used the math formula with a 3D printer to print those. Okay, so there's a real mathematical formula which produces an s orbital. There's a real one that produces a p orbital. Now here's where you have to trust me. If we add those mathematical formulas together, more math, we do a bunch of math and add them together, we end up with 2 new orbitals, 2 hybrid orbitals that are sort of a combination of them. And I'm going to draw them in the same spot. Okay, in other words, they're on the same atom. This is showing the 2 orbitals. This is what happens if the beryllium atom is sitting in the middle. You end up with an orbital, one lobe that comes out this way, and with a little guy in the back. That's this one right here. Okay, big orbital with a little guy in the back. And then we end up with another one, big orbital with a little guy in the back. Now, of course, the little guy in the back just gets sort of absorbed into the big guy. So we end up with a hybrid orbital. Looks kind of like a p orbital, but these are actually 2 hybrid orbitals. Hybrid orbital number 1 and hybrid orbital number 2. Okay, 2 hybrid orbitals. That's what these 2 things represent. You know, we call this number 1 and then number 2. All right, and there's an electron in each of those guys. 1 electron present in each of those orbitals. There's no electrons in the p orbitals. All right, now along comes hydrogen on this side, hydrogen on this side, and that has a 1s1 electron. Both of them have a 1s1 electron. Now remember what a 1s orbital looks like. A 1s looks like a sphere. So that guy comes along, arrow pointing down, overlaps with the orbital, with the hybrid orbital, and forms an overlap in between those 2 atoms. Okay? Hydrogen's got an extra electron. It sees a slot where it can fill into. This hydrogen has an extra electron. It sees a slot where it can fill into. It's able to share those 2 electrons, and it's able to share the space between the 2 atoms, and that creates a chemical bond. So there's a way to describe this. We tell what types of orbitals are overlapping to form this bond. So we would say this is an sp1s covalent bond, and this is an sp1s covalent bond. All right, and I'm going to give you one more name. I already told you what this is, but this is called a sigma bond. So we would say this is a 1s, sp1s sigma bond. There's two of them in this particular molecule. And it's the overlapping or the sharing of electron, one from an S and one from one of the sp hybrids, an sp hybrid overlapping with one of the S's. Okay, that's what forms my BeH2. And by the way, do you notice the angles of these? This forms a 180-degree angle. So this solves the problem of the other one suggesting it should be 90-degree angles when it really should be 180 degrees. Okay, so the geometry is better, the bonding makes more sense, and the fact that we've got two electrons to share and the reason why I can violate the octet rule all gets explained by this model. All right, what about sp2 hybridization? Let's take boron trifluoride. Fortunately, boron trifluoride is another one that violates the octet rule. You may have wondered, why does it violate the octet rule? Here's the reason. All right, what was my notation was orange for unfilled, I think. Yeah, orange for unfilled, or orange for atomic. So let's get my orange pen out. So I'm talking about the boron atom now here. So this is a 2s2 2p1. That is the atomic orbital. Now, if you're looking at that, you're saying, okay, I've got one to share here. I can form one bond, but I've only got one electron I can share from boron. So how do we deal with this? Well, remember, if we use my cheating rule, we say, all right, this has 3 electron domains, therefore it's trigonal planar, therefore it must be sp2 hybridized. What does sp2 hybridized mean? It means one s orbital is combining with 2 p orbitals to form a new set of hybrid orbitals, 3 hybrid orbitals. And I've got 1 p orbital left over. And I put one of those electrons from the s into the new hybrid orbital. Okay, so I've got an sp2 and I've got a p orbital left over. Now you can see, hey, wait a minute. That guy, whoops, keep doing that. That guy's got 3 slots it wants to share with some other atom. It's got 3 places it wants to combine. Now, how does this work out as far as geometry is concerned? Well, same thing. I have an s orbital, sphere. I've got 2 p orbitals. This one happens to be an x and a y. It doesn't matter. If I add those together mathematically, you're just going to believe me that this happens. But we end up with 3 new hybrid orbitals looking down from the top. One of them looks like this. One of them looks like this. One of them looks like this is a top view of these 3. And guess what the angles are on that? 120 degrees apart. This is in my hybrid orbitals. Okay? And that forms a trigonal planar structure. So to form the bond then, fluorine is 2s2 2p5. 1, 2, 3, 4, 5. It's got 1 electron that wants to combine. I've got 3 of these guys, and it can say, hey, wait a minute, that guy could match up with one of these, and I've got 3 of them, so I can match up all 3 of these. And notice this is coming from a p orbital, the one that's looking for someone to bond with. So I can get a p orbital here from one of the fluorines. I can get a p orbital here from one of the fluorines, and I can get a p orbital here from one of the fluorines. Each one of these is contributing 1 electron, and then this guy has 1 electron. Whoops, trying to color code these. This guy has an electron in there, so it overlaps in between the 2 atoms. All right, now let's see. We'll stop this video here. You can stop the video and see if you can tell me what would we call that single bond. What orbitals would describe that single bond? Actually, all 3 of them are the same. So if you want to stop it right now and see if you can figure that out. So that bond would be called an sp2 2p sigma bond. Just like that is, just like that is. All right? It's the overlap of a p orbital from the fluorine with an sp hybrid from the boron. And 3 of those get formed. Trigonal planar, that explains the geometry. That helps match up these extra electrons from the boron. That's how the 3 boron electrons can get involved in a chemical bond. And that explains how this fluorine electron can get involved as well. All right, sp3 hybridization. I'm not going to go through all the math, explain that again, except to say that now let's take carbon as my classic example. Carbon's atomic orbitals look like this: 1, 2, 3, 4. Looks like I have 2 slots to fill, not 3, and these should be 90 degrees apart, and we got one empty one. So how do we fix that problem? Well, now let's take a molecule like CH4. It's got 4 domains. Remember, the Lewis structure looks like this. So it's got 4 electron domains around it, 4 electron groups, and that means it's tetrahedral, and that means it's sp3 hybridized. So what does that mean? That means the sp orbital combines with all 3 p orbitals to form 4 new hybrid orbitals. Do you notice that the number of hybrid orbitals is equal to the number that combined? Okay, so 3 p orbitals combined with 1 s orbital to get 4 new orbitals. And these all are going to have 1 electron, which explains why carbon likes to form 4 bonds, right? Got 4 slots that want to be filled. And trust me on this, do the math. We get 4 new orbitals. If we combine them all into one place, they end up being tetrahedrally shaped, which is why we end up with tetrahedrally shaped molecules. If I want to sketch my carbon, it's got an orbital here with a little tail on it. It's got an orbital here with a little tail on it. It's got an orbital here with a little tail on it. It's got another one back behind with a little tail on it. This isn't the best drawing in the world. Each one of these has an electron, and along comes a hydrogen and overlaps each of these lobes with an electron of its own to form a chemical bond in between each of these. All right, you want to stop it and see if you can say what the name of this bond is, or what orbitals make up that bond? Feel free. Okay, so that would be called a sp3 1s sigma bond. And all 3 of these, or excuse me, all 4 of these have the same type of bond. 4 sigma bonds, all of them sp3 1s for this molecule. All right, so we've already talked about this example. Save you a little bit of time here. This is the boron trifluoride example that we had, that I showed you a few minutes ago. And just want you to recognize the p orbital is what's contributing from the fluorine, and the boron has the sp hybrids. We just talked about methane, CH4. We just explained how that works. So let's take a look at a molecule that doesn't have everything filled, okay, because it's pretty common. So let's take a look at NH3, ammonia. All right, so Lewis structure for ammonia, if you want to stop your video and practice it, looks something like this. 4 electron domains, right? 4 bonds, 1, 2, 3, 4. Therefore, hybridization, sp3. All right, so that means, and I'm just going to write the hybrid orbitals now. I'm not going to bother writing them hybridizing. It's sp3 hybridized, which means I've got 4 total orbitals, and now I've got 5 electrons. 1, 2, 3, 4, 5. So you notice something different about this one? I've got a lone pair of electrons, or I've got a pair of electrons that are already paired, and then I've got 3 slots that want to form bonds, which makes sense. Nitrogen's already forming 3 bonds. But that double one there is representing the lone pair. Can't form any more bonds. That's the lone pair that's being formed, is the 2 that are being shared with each other. So what does that look like in terms of the hybrid molecule or hybrid orbitals? Well, I've got 1 with a little tail in the back, 1 with a little tail in the back, 1 with a little tail in the back, and 1 here with a little tail in the back. There's my lone pairs on one of them. Put a little smiley face on it. Okay, I'm getting a little crazy here. All right, 1 electron from each of these. And this guy actually, maybe not a smiley face until it fills all its orbitals in. So right now it's sort of like a weird looking octopus. But it's going to combine with hydrogen, 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 electron from each of those. And now this guy's going to have a smiley face. Okay, stop and tell me what kind of bonds these are. You got it. sp3 1s bond is formed. All 3 of these are sp3 1s. That's what this picture is showing you. There's the hydrogen, there's the NH3, that bond right there, that bond right there, and that bond right there are all sp3 1s, forming the chemical bond. All right, and the lone pair is this guy right here. That's the lone pair in the hybridized nitrogen. All right, how about water? Kind of important molecule. H2O, there's the Lewis structure. Completely legit Lewis structure. It does not show the geometry. Why not? Well, there's 4 electron domains. That means it's really tetrahedral, the electron pair geometry. So it really looks something like that. We call the molecular geometry a bent geometry. Why do I worry about the electron pair? That tells me how many electron regions are, how many groups there are. 4 electron groups. Therefore, this guy is sp3 hybrid. All right, and we're going to write out the sp3 hybrid structure for the oxygen. That's the central atom, right? 1, 2, 3, 4, 5, 6 electrons. Whoops, did it again. 6 electrons, 2 slots that want to be filled, 2 lone pairs, 1 and 2. 2 lone pairs in the oxygen, that's those 2 extra lines, and 2 slots that want to be filled. We know that water, put an oxygen here, we're going to draw 1 orbital there, 1 orbital there, and put another one up here, smiley face on it, another one back here. Maybe this one isn't quite as happy because it's sitting in the back here. All right, and these guys both have electrons, and they are going to combine with, I guess I should put the arrow down to pair with it. This is a hydrogen, this is a hydrogen. And what do you think the bonding is? sp3, 1s, again, that guy and that guy. Okay, sigma bond. All right, this one should be sigma bond. All these should be sigma bond. Sigma bond, sigma bond. Okay, every one of these that I've drawn so far are sigma bonds. All right, so what is a sigma bond? So a sigma bond is when the electron density is in the middle between the 2 atoms. Okay, all the electrons are being located between the centers of the 2 atoms. That's what this picture is trying to show you in my cruddy drawing, right? Electron density in between the 2 atoms. All these, every single one of these has been a sigma bond. So electron density between the 2 atoms we call a sigma bond. So what's a pi bond? All right, so let's take an example that's a little more complicated. Lewis structure that we drew earlier. I'm just going to start by drawing the geometry correctly on this. Central atom sp2 hybridized. Oxygen actually also sp2 hybridized. Can you tell me why? 1, 2, 3 electron groups around it. All right, so let's draw this from the perspective of the carbon. First, let's draw where the electrons are in the carbon. It's sp2 hybridized. Actually, let me erase this because that's not going to be sp2. Let's go sp2 hybridized, which means 3 orbitals, 3 hybrid orbitals, and 1 extra p orbital. And the carbon has 4 electrons, so I got to put 1, 2, 3, 4 in there. So we got an sp2, and we have another p orbital. Now you notice in these other ones, when I was drawing that extra p orbital, they were empty. This one's full. Okay, this one we're not full, it has an electron. So there's some slots available. 1, 2, 3, 4 slots are available. Okay, and let's say this is the carbon. Now, the oxygen is also sp2 hybridized. So it looks exactly the same. 1, 2, 3, and an extra one. It's got 4 slots that want to be formed. So how does it look like from the carbon's perspective? So here's the carbon. And I'm going to draw an XYZ coordinate system, and maybe I should switch colors for oxygen. Okay, so I have an oxygen and a carbon. And I know I've got, actually I don't have enough electrons there, do I? All right, I'm going to make this more explicit. Oxygen's going to be orange now. I've got 6, I should have 6 electrons for oxygen. 1, 2, 3, 4, 5, 6. The 2 lone pairs are in sp hybrid orbitals. They're not in the p orbital because they're equivalent to each other, so they have to be the same. All right, so I'm going to sketch these hybrid orbitals. I'm going to draw one there with a little guy in the back, one guy coming back with a little front, one guy coming this way with a little front, and I'm going to put a lone pair there, a lone pair there, and I'm going to have 1 electron in the middle. Okay? Now you might be saying to yourself, okay, you've taken care of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. You're taking care of 5 electrons. What about this p orbital? This p electron wants to be as far away from these other electrons as possible. And the way it does that is it's a p orbital, right? It's going to stay a p orbital. It's going to be a dumbbell shape. But it's going to be out of that plane. That's a trigonal planar structure, sp2. So it's going to stay out of the plane. So that p orbital is going to be sticking above and below the plane. And same deal with the carbon. Okay, so carbon's got sp orbital, sp2, sp2, sp2. It's got 3 sp2 hybrid orbitals. That's what this is right here. All right, and it's got electrons in all those sp2 orbitals. So where can the overlap occur? Right in between the 2 of those guys. But it's also got a p orbital. And p orbital's got an electron in it. Okay? So these guys interact with each other. The lobes of those p orbitals can overlap with one another. I haven't drawn them like this, but maybe I should draw them a little more, a little bigger than this. Actually, what happens is the atoms end up closer together, which is why a double bond is shorter than a single bond. Okay, so these have different names now, right? And we got to draw one more thing, and then we'll talk about that. So I need to put the hydrogens on here. This is just like all the other ones we've had. All right, so let's give some names to these. How would you describe that bond right there? You can stop. And by the way, this one's the same. How would you describe those? So we would say this is an sp2, 1s sigma bond. Both of those are that sp2, 1s sigma bond. How would we describe this bond right here, the one in the middle between the carbon and the oxygen? How would we describe that guy? That guy is an sp2, sp2 sigma bond. Remember what I said the definition of a sigma bond is. Sigma bond is electron density between the two atoms. That's this guy right here in this drawing up in the corner. Okay, I know I'm scribbling all over this thing, it's hard to see. But the guy in between the two is the sp2-sp2 sigma bond. This guy here, the overlap above and below the plane, that one is called a pi bond. You think of pi because it comes from a p orbital. So that bond is called a pi bond. Now don't be fooled by the fact that I drew two lines. There's only one pi bond here. It's just the two lobes of the p orbital are overlapping with one another. Okay? So we would describe the pi bond as a 2p, 2p pi bond. That's this picture right here. That's a lobe of the pi bond. That's the lobe of the pi bond. Okay, these are unhybridized p orbitals. The middle one is the hybrid orbital. The pi bonds are the unhybridized pi orbitals. All right, here's another picture, a little more sophisticated model. This compares a CH4Cl2 molecule, and these are all sp3 hybridized carbons, and the bonds can actually rotate. If you actually made these models in lab, I don't know if everyone did or not, if you made the models in lab, you can find that a single bond you can rotate. Double bond, you have to use the springs to make it. Those don't rotate. That's actually true in molecules. Double bonds do not rotate around the atoms. Single bonds do. That's why those model kits are kind of nice. All right, so this molecule right here has one pi bond. How many sigmas? 1, 2, 3, 4, 5 sigmas. Okay, and if you want to name those, that is a sp2 3p orbital. It's a chlorine atom. This one's an sp2 1s orbital. It's the same thing over here. All right? Okay, let's take one more and then we'll be done. Let's take a look at this molecule right here called acetylene. Triple bond between the carbon. This has two electron groups. One here, one here. So therefore, hybridization, sp hybrid on that guy, sp hybrid on that guy. So what does an sp hybrid look like for carbon? Sp means I took one p orbital and borrowed it. I've got 4 total valence electrons. And now I've got 2 unhybridized and 2 hybrid orbitals. Okay, so I'm going to sketch this. This is going to be a crazy, crazy drawing right here. Do my best. Here's a carbon. Here's another carbon. Remember what the sp hybrids look like. They look like a dumbbell with a little guy in the back. And, oops. And another dumbbell with a little guy in the back. So it kind of looks like a p orbital, but it's actually 2 orbitals, not 1. So we already know this is sp hybrid. So that guy's going to have one of those, little guy in the back, one of those with a little guy in the back. It's got an electron in each. And the other carbon has dumbbell, little guy in the back, dumbbell, little guy in the back. It also has 2 electrons. Okay, so that forms an overlap. What do we call that overlap? sp, sp, sigma bond. Overlapping in between the 2 of them. All right, let's take care of the hydrogens. Those are easy. We've done a bunch of those. Those are easy to see. Hydrogen here, hanging off the backside. Just to be consistent with my drawing here, this one's going to have an arrow up, this one has an arrow down. Doesn't really matter, that's not important. Got an overlap there, overlap there. What do we call that bond? I'll stop it and write down what it is. That one is an sp1s sigma bond. All right, now we've got 2 more electrons to deal with on each carbon. Each carbon is the same situation, right? 2 more to deal with. So this guy has a p orbital. It's trying to be as far away from the other ones. Along these 2 axes, there's p orbitals, and there's 1 electron in each of those p orbitals. And this guy, oh, what color should I use? Pink. That's nice. Blues and pinks. Has 1 here and 1 here. And that's got 2 electrons unhybridized. And guess what they do? They overlap with one another. The ones that are along, let's say this is the z-axis. The ones that are along the z-axis overlap with one another. And the ones that are along the y-axis, we call this the y-axis, they overlap with one another. Now look, my drawing's getting ridiculous. This is a much better picture right here. Right? But basically what we end up with is 2 p orbitals that overlap, 2 different p orbitals. So that type of bond is called a pi bond. That's pi bond number 1, and there's pi bond number 2. That's the overlap of 2 unhybridized p orbitals. All right, so this guy has 1, 2, 3 sigma bonds, 2 pi bonds. Now look, it's not super obvious, and by the way, these would be p pi bond, the overlap for them. Specifically a 2p, this carbon has 2p electrons. This isn't real obvious at this point. It's not really that important for Gen Chem. Wow, this is a crazy drawing. But when you get to organic chemistry, you're going to realize that's where electrons are. And there's space for other molecules to come in here and attack those electrons. So double bonds and triple bonds are very reactive. You can get a lot of chemistry to happen at double bonds and triple bonds. All right, so let's just do a quick recap. Start with a formula. So let's just make some up. C2H4. Draw a Lewis structure. That's going to look something like this. Look, I've drawn this molecule a lot. I know what it is. It might take you a little bit longer. That's fine. Okay, now we can analyze each individual central atom and say, what's the geometry of these guys? The molecular or the electron pair geometry, not the molecular geometry. So we count up electron groups, 1, 2, 3 on this one, 1, 2, 3 on this one. From the electron group geometry, so electron group geometry, we can determine the hybridization. So this one is sp2, and this one is also sp2. sp2 hybrid for both of them. From the hybridization, we can figure out what the types of bonds there are. So this is going to be 1, 2, 3, 4, 5 sigma, 1 pi. All of these bonds are sp2 1s bonds. This guy, the sigma bond, is sp2 sp2, and the pi bond is 2p 2p. Now look, it doesn't matter that I drew this to the bottom line. That doesn't mean anything. Okay, it just means there's 1 sigma bond, 1 pi bond. All right. From the Lewis structure, we can figure the electron group geometry, we can figure the hybridization, and now we can understand more about the bonds. We also can understand why double and triple bonds are shorter, because they have to be closer together for those things to interact. We also can understand why they're stronger. You have to break 2 sets of bonds or 3 sets of bonds for a triple bond in order to break them. Explains the bond length, explains the bond strength. We've got a much better model than we had originally. All right, team, you have made it to the end of Gen Chem 1. Congratulations. Thanks for hanging in there with me. Hopefully this will work. Hopefully I'll be able to upload it and you'll be able to hear my lovely voice. And I will see you next week and see you for the final exam. All right. Cheers.